So in this video, we're going to look at probability with events involving not and then or. So or probabilities, not probabilities. Then we'll also look at odds at the end of this video. Okay. So I am on the tablet, so it'll be slightly easier to see. But it's always a little awkward when I'm shifting. So give me just a second to get to the whiteboard. Okay. So we're going to deal with probability of events involving not and or, and then we'll also talk about odds. Okay, so first we've got some definitions and some notation that we have to learn. So the first thing we have is the complement of an event E is the event not E. So we're going to be looking at events and the probability that they don't happen. Okay, so basically looking at the probability of an event not happening. So if you were talking about rolling a die, we could say, what is the probability that you would not roll a 3? Well, how many ways could you not roll a 3? That would be the probability we were looking for. Okay, so another thing we have to look at is how that we would note this. Okay, so if I have the probability of not E, that is 1 minus the probability of E. Okay, so this right here, pretty big. Okay, so basically the probability that an event does not occur is the probability, well, let me rewrite that, is 1 minus so it's 1 minus the probability that the event does occur. All right, so I think the best way to deal with this is just to look at some examples. Okay, so let's say for the first example, we are dealt one card from a standard 52 card deck. Find the probability of not being dealt a spade. So we want the probability of not a spade. Okay, well, that is 1 minus the probability that we do get a spade. So we're going to get 1 minus, well, if you're dealing with a 52 card deck, how many spades are in the deck? Well, there are 4 suits in a deck. Each suit has 13 cards. So the probability that you are dealt a spade would be 13 out of 52. So we're basically taking 52 over 52. We're going to subtract 13 over 52. Whoops. And so that would give us 39 over 52, or 3/4. And that kind of makes sense. If 1/4 of the deck is a spade, then that would mean 3/4 of the deck is not a spade. Okay, let's look at another example. So you roll a die, find the probability of not rolling a 3. Well, it's 1 minus the probability that you do roll a 3. So how many ways in a fair 6-sided die could you roll a 3? Well, 1 out of 6. So we basically get 6, 6, that's the 1, minus 1, 6, which gives us 5, 6. And that should make sense. If 1 out of 6 sides of the die is a 3, that means 5 out of 6 sides of the die would not be a 3. Okay, so make sure you understand how to do the not probabilities. Okay, it's just 1 minus the probability that the event does occur. All right, next, let's talk about or probabilities. Now, this is going to be broken down into two types of probability. You're going to have a situation where you're dealing with mutually exclusive events or events that are not mutually exclusive. So first of all, we have if it is not possible for events A and B to occur simultaneously, the events are said to be mutually exclusive. So that's kind of the first definition. The second definition, which it's not listed in the same spot on your worksheet, but I want to go ahead and go over it just kind of right now. If events could occur simultaneously, the events are not mutually exclusive. So basically, if two things could happen at the same time, they're not mutually exclusive. If they could never happen at the same time, they are mutually exclusive. So an example of mutually exclusive events, drawing an ace or a king from a 52 card deck. These two things can never happen at the same time. There's no card that is simultaneously an ace and a king. Okay, you're either drawing an ace or you're drawing a king. There's no overlap between those two cards. Those events would be mutually exclusive. Now, a situation that would not be mutually exclusive would be drawing a king or a heart. We have overlap, which means these events are not mutually exclusive, okay? There is a card in a deck that is simultaneously a king and a heart. It's the King of Hearts, okay? So if there's no way the two events could happen at the same time, we say they're mutually exclusive. If there's overlap, we say they're not mutually exclusive, okay? So just kind of understand the difference between mutually exclusive and not mutually exclusive, okay? Now, as far as the probabilities when we're dealing with OR, we have the following setup, okay? So if A and B are mutually exclusive, then the probability of A or B is the probability of A plus the probability of B. So when you're looking for that OR probability, I feel like a sneeze is coming. Please excuse me if it happens. Sorry about that. Couldn't avoid it. Okay, so when you're dealing with probabilities with OR, you will flat out see the word OR in the problem, okay? You then have to decide if your events are mutually exclusive or not, okay? For mutually exclusive events, you take the probability of A and you simply add it to the probability of B, okay? So for the first example, we're going to roll a single 6-sided die, find the probability of getting either a 4 or a 5. Okay, so first of all, we have the word OR. So that tells us we're doing the OR probabilities, which I think is fairly obvious. When you're dealing with OR probabilities, you simply add. So we're looking for the probability of rolling a 4 or a 5. That is the probability of rolling a 4 plus the probability of rolling a 5. And if you're dealing with a fair 6-sided die, the probability of landing on a 4 is 1/6. The probability of landing on a 5 is also 1/6. So we would have a probability of 2/6, or if we simplified it, 1/3. So there you have it. All right. Now, another example, we're going to be drawing from a standard 52 card deck. What is the probability? of drawing a 4 or a queen. Well, are these events mutually exclusive? Absolutely. There's no card that is simultaneously a 4 and a queen. You either have a card that has a 4 on it, or you have a card that has a queen on it. So we want the probability of a 4 or a queen, which is the probability of drawing a 4 plus the probability of drawing a queen. Now, the probability of drawing a 4 in a standard 52 card deck, there are 4 cards with a 4 on them. There's the 4 of hearts, the 4 of diamonds, the 4 of spades, and the 4 of clubs. So 4 out of 52 cards are 4s. And then with the queens, same thing. There are 4 queens in a deck. There's the queen of hearts, the queen of diamonds, the queen of clubs, and the queen of spades. So if we add these two probabilities, we get 8 out of 52. And then you always want to reduce your fraction, and you can reduce it on the calculator. Let's see, 52 and 8 are both divisible by 4. So we would get 2/13. So the probability that you would draw a 4 or a queen out of a standard 52 card deck is 2/13. Okay, let's look at not mutually exclusive events. So if A and B are not mutually exclusive, and I do think you need to fill in the word not mutually exclusive here. Your notes said I think there's a typo and the word not is not included, so you need to put the word not in there. So if A and B are not mutually exclusive, then the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. This is your overlap. So basically, you're taking the probability of the two events and you're adding them. But when things are not mutually exclusive, there's overlap, okay? So we always want to subtract the overlap. And this is going to make a little bit more sense when you see it with an example, okay? So for the first example, we're dealt one card from a standard 52 card deck. What is the probability of being dealt a 3 or a heart? So we want the probability of drawing a 3 or a heart. So that's going to be the probability of a 3 plus the probability of a heart minus the probability of the overlap. Okay, so the probability of a 3 in a standard 52 card deck, there are 4 cards with a 3 on them. There's the 3 of hearts, the 3 of clubs, the 3 of diamonds, and the 3 of spades. So we get 4 out of 52. And then when it comes to hearts, there are 13 hearts. Remember, there are 4 suits in a deck. Each suit has 13 cards, so there are 13 hearts. But we have to subtract the overlap. In this case, the overlap is the 3 of hearts. Let me write that out in words. So this 3 is being counted here with the 3s, and it's being counted here with the hearts. You can't count it twice. So we have to subtract that 1 card out of 52 that's got the overlap because it's being counted 2 times. So what we're going to do here is we're going to take 4 plus 13 plus 1. We're going to put it over 52. So that's going to give us 16. Whoops, I got to subtract. I forgot to subtract. There we go. So that's going to give me 16 over 52. And then we always want to reduce it. 16 and 52 are both divisible by 4. So the probability that you are going to be drawing a heart or a 3 is 4 out of 13. Okay. Again, you want the probability of I think I said the probability of drawing a 4 or a heart. The probability of drawing a 3 or a heart is going to be 4 out of 13. You take the probability that you draw a 3, you add it to the probability that you draw a heart, and then you subtract the overlap. Okay. For the next example, let's look at rolling a die again. So what is the probability? Of rolling a 3 or an odd number. So we want the probability of a 3 or an odd. So that's going to be the probability of a 3 plus the probability of an odd minus the probability of the overlap. So when you're dealing with a fair six-sided die, there is one way to draw or to roll a 3. As far as odd numbers go, you've got 6 sides to the die, 1, 2, 3, 4, 5, and 6. Of those 6 sides, 1, 3, and 5 are odds. So we have 3 out of 6 ways to roll an odd. And then of those, you've got a situation where one side meets both criteria. So a 3, obviously it gives you the 3, but it's also an odd number. So we have to subtract the overlap. So in this particular case, we simplify, we get 3 out of 6 or 1/2. So the probability of rolling a 3 or an odd number on a fair six-sided die is going to be 1/2. Now, I should have used my laptop because of this next example right here, but I decided to go ahead and use the tablet because you've seen this table before, okay? We have, and I'm going to kind of redo the table here just sort of quickly. We have a situation where we have a table of real values, okay? So this is the empirical versus the theoretical probability that we talked about in a previous video. But in this table, we have the marital status of the US population in 2015. Numbers are expressed in millions. So the table is broken down into male, female, and total. And then we have married, never married, we have divorced, we have widowed, and then we have totals again. Okay, so married men were 66 million, women were 67 million, the total was 133 million. Never married, 43 for males, 38 for females, 81 total. 11 million male divorcees, however you say it, 15 million females were divorced, 26 million total. Widowed, 3 million men, 11 million women, 14 million total. And then for the totals, for males, there were 123 million men represented, 131 million women, and 254 people represented in this table total. Okay? And remember last time I did some of this in colors. All right, I'm not going to go straight to the colors now, but if necessary, I will look at them in a minute. So the problem here says if one person is randomly selected from the group, find the probability of the following. So we're just going to say find each probability. The first probability we want to look at is the probability that somebody is married or female. Now on this problem, the directions do not specify if we're supposed to do a fraction or a decimal, so we're going to represent our answer in both ways, okay? But first, let's decide if the married or the female would be mutually exclusive events. So you have to ask yourself, is there a chance that a woman could be married and female? Well, of course. So what we want to do is we want to take the probability that somebody is married, add it to the probability that somebody is female, and then we're going to subtract the probability of any overlap. So that would be the women that are married. So the probability that somebody is married, that's 133 million out of the grand total of 254. The probability that somebody is female is 131 million out of 254. But out of that, some of those are both women and married. So we have to subtract the overlap. The overlap is 67 million women that meet both criteria. So those 67 million women, they're considered in both of these probabilities. So we have to subtract them out so they don't get counted twice. So what I want to do here is I'm going to add 133 to 131. I'm going to subtract 67. All of that goes over 254. When I subtract that, I get 197 out of 254. And then I'm going to go ahead and write this as a decimal rounded to 2 decimal places. So we get 0.78. So the probability that you select one woman from this or one person from this table, the probability that you get a woman or somebody married is 0.78% or 0.78, so 78%. Next up, we want to look at the probability that somebody is divorced or widowed. Now, this one is a little bit tricky because we're looking at a current marital status. So the most recent marital status. So yes, somebody could have had a divorce and could have been a widow in their past. Okay, but we're looking at the most current one. So if somebody was divorced when they were younger and then at a much older age, their spouse died and they were then like on their second marriage, their spouse died and they were then a widow, we're going to count the most recent one. So could somebody simultaneously be divorced or widowed? No, because you're only counted in this table at your current marital status. Okay, so divorced or widowed, there's no overlap here. So these events would be considered mutually exclusive. So we want the probability of divorced Americans plus the probability of widowed Americans. So again, don't think about this too deeply. Just know we're talking about the most recent marital situation for each person in this table. So the probability that somebody is divorced would be 26% or 26 million. There are 14 million widowed people in this table. So we would get 26 out of 254 plus 14 out of 254. That's going to give us 40 out of 254 million. We could reduce that and you could just use your calculator to reduce, which would be 20 over 127. And then let's go ahead and write it as a decimal. So approximately 0.16 or 16% of the table would be considered divorced or widowed. So if you select one person from this table, the probability that they're divorced or widowed would be 16%. Let's do the next one. So C, we want divorced or male. Now the question is, could somebody simultaneously be divorced and male? Absolutely. Okay, so we're looking at divorced, which is 26 million of the people in the table. We're looking at males, which is 123 million in the table, but you can have males that are also divorced. That's 11 million from the table. So what we want is we want the probability of divorced plus the probability of male minus the probability of the overlap. Those are the males that are also divorced. So the probability that somebody's divorced, we want the total divorced people in this. So that's 26 million out of 254. We want the total number of males. That's 123 million out of 254. But the males that are simultaneously divorced, they're being counted in both of these probabilities. So you have to subtract it because you only want to count it once. So we're going to subtract the males that are divorced. Now what that's going to give me is 26 plus 123 minus 11 out of 254. So that's going to give me 138 out of 254. If you reduce this, you can use your calculator. You would get 69 out of not 69 out of 254. Hold on. I've got a mistake on my sheet. So you get 69 out of 127. And then if we write that as a decimal, we would get 0.54. So approximately 54% of this table is male or divorced. So again, if you choose one person at random, the probability of getting somebody that is male or divorced would be 54 million. Now, the last example, we have married or divorced. So remember, this is kind of like the widowed or divorced. We're looking at the most recent marital status. Yes, you could have somebody that at some point in the past had a divorce and then they remarried. Of course, that could happen. But we're only looking at the most current marital status. So somebody cannot simultaneously be married and divorced. They could have a previous divorce, but then they're currently married. Okay, so looking at this table, the people that are married, that's 133 million. The people that are divorced, that is 26 million. There's no overlap here. So we're going to take the probability that somebody's married. We're going to add it to the probability that somebody's divorced. There's no overlap. So we're going to get 133 out of 254 plus 26 out of 254. All right. And then when we add that up, let's see, we get 159 out of 254. That does not reduce, but we can write it as a decimal and we would get 0.63. So flipping coins, dealing with like game spinners. And then you've got the empirical probability. Remember, empirical probability is what is actually observed. So you're looking at real data, generally in some kind of table form. Okay? All right, let's look at odds. Okay? So when you're talking about odds, you're looking at the odds in favor or the odds against an event occurring. Okay? So let's see, if you have the probability of event E, so if P of E is the probability of an event E occurring, sometimes occurring, then here are the two formulas you need to remember. Okay, so that was kind of a mess, but basically, if P of E is the probability of an event occurring, then the odds in favor of E would be the probability that E occurs divided by the probability that E does not occur. And then you could have the odds against E, and that's going to be the probability that E does not occur divided by the probability that E does occur. Okay, so we need to look at some examples of this. So I'm going to do the first example on this slide so you can see the formulas. So we're going to deal with a deck of cards. So you're going to be dealt one card from a standard 52 card deck. What we're going to do first is find the odds in favor of getting a red queen. Okay, so we want the probability of getting a red queen divided by the probability of not a red queen. Okay, so in a standard 52 card deck, how many cards would be red queens? Well, we've got 4 queens total, but only 2 of them are red. We have the Queen of Hearts and the Queen of Diamonds. So the probability that we do get a red queen would be 2 out of 52. Now that means there are 50 cards in a deck that are not queens, that are red. So you have 50 ways out of 52 to not draw a red queen. Now I'm going to show you the long drawn out version of this, and then I'm going to show you the shortcut. So technically we have 2 out of 52 divided by 50 out of 52. When you're dividing fractions, the first fraction stays the same, and then you multiply by the reciprocal of the second fraction. So you just flip the second fraction. And in this case, the 52s cancel. We're left with 2 out of 50, or 1 to 25. So we would say the odds are 1 to 25. Okay? Now, look at this. Basically, what ended up happening, instead of doing this long division, the denominators are always going to cancel out, and you're just left with the numerators. So you're just looking for the ways it does happen and divide it by the ways it does not happen. Ways it does not happen. Or that's for odds in favor. If you do the odds against, you would want the ways it doesn't happen divided by the ways it does happen. All right, so you don't have to do the full fraction thing if you don't want. You can just jump to this, to like how many ways it does or does not happen. So let's look at another example. So let's find the odds against. I'm going to go back to the black ink. So we're going to find the odds against a red queen. Now remember, this is going to be the probability that the event does not occur divided by the probability that it does. So we want the ways that you could get a red queen versus the ways you don't get a red queen. Okay, so how many ways could you get a red queen? Well, there are two ways to draw a red queen. That's the queen of hearts and the queen of diamonds. That leaves 50 cards that are not red queens. So that's really all you have to do is figure out the ways it does happen versus the ways it doesn't happen, and just remember which one goes in the numerator for each situation. So we reduce this and we get 25 to 1, or you can write it like this, 25 to 1. Okay? And we read it like this, 25 to 1. Okay? So that's it. Let's do a bonus example. What are the odds in favor of drawing a spade? Okay, so when you're dealing with odds in favor, we want the probability that you do draw a spade divided by the probability that you don't draw a spade. So how many ways could you draw a spade? Well, in a regular 52 card deck, there are 13 spades. And then the way that we would not draw a spade would be, well, if you've got 52 cards and you know 13 of them are spades, that means 39 are not. So this reduces to 1/3 or 1 to 3. So for every spade, there are 3 cards that are not spades. Let's do another bonus example. Let's do the odds against a face card. Okay, so that's going to be the probability that you don't get a face, because we're doing odds against, divided by the probability you do get a face. Now ask ourselves, how many ways do we draw a face card? Well, face cards are queens, kings, and jacks. There are 3 face cards for each suit. There are 4 suits. So that means there are 12 face cards. Now, if there are 12 face cards and there are 52 cards total, if 12 of them are faces, 40 of them are not. Okay? So we would take that 40 ways to not draw a face card, 12 ways to draw a face card. You would reduce this to 10 over 3. Both 40 and 12 are divisible by 4. So we would say 10 to 3. So for every 10 cards that are not faces, there are 13 cards that are. Okay. So again, you got a couple of bonus episodes. Good grief. I've watched too much TV. You've got a couple of bonus examples here to understand odds in favor versus odds against. Okay. Let's do a couple more examples. So we have a word problem where we have the winner of a raffle will receive a 2-year scholarship to the college of his or her choice. We have 1,000 raffle tickets sold. Okay. You purchased 5 of them. So we have this raffle where you receive a 2-year scholarship to the college of your choice. 1,000 raffle tickets have been sold. You purchased 5. What we're looking for is what are the odds against you winning. All right. So we want the probability that you don't win. We're going to call it not win, just we're using the same like wording, versus the probability that you do win. Now, you bought 5 tickets, okay? The probability of you winning would be 5 out of 1,000. So there's 5 ways that you could win, but that means there are 995 ways that you could lose. We simplify that. And in this particular case, there are 199 to 1. All right. Next up, we want the probability, where we're going to go from odds to probability. You know what? I just thought of this. I think I've made a goof. So you bought 5 tickets, but let's go back to the raffle problem. So you've got the probability that you don't win versus the probability that you do win. There's only one winning ticket. It doesn't matter how many you bought. So there's one way to win versus 999 ways to lose. So there would be 999 to 1. So that means for every 999 losers, there's one winner. Okay. Sorry about that. I just had like this moment, this like lapsing moment for just a second. Okay. So let's go odds to probability. So assume you're given odds, but you need to find the probability. So if the odds in favor, make note we're talking in favor of event E are A to B, then the probability of the event is given by A over A plus B. So they're going to give you the odds. The odds are A to B. So there are A ways it could happen compared to B ways it does not happen. So you get the probability A to B. Now, if you have the odds against, it's going to be reversed. It's going to be B to A. So that would change things slightly. It would be B over A to B in that particular case. All right. So let's look at an example. It says the odds, well, let me go to the next screen. The odds against a particular horse. Wow. I can't spell. That one was bad too. So horse winning a race are 15 to 1. Now keep in mind, this is the odds against. Find the odds in favor of the horse winning. Good grief, I can't spell horse to save my life. Of the horse winning the race and the probability of the horse winning the race. Okay, so in this particular case, we're given the odds against. So the odds against the horse were 15 to 1. That means the odds in favor are going to be the reverse of that. It's going to be 1 to 15. Okay, so then we already know that if the odds in favor are 1 to 15, this is like our A, this is like our B. And we could have the probability of that being A over A plus B. So the probability of the horse winning is going to be A, the way it wins, over the sum of the way it wins or loses. So it's 1 over 16. So the probability the horse wins is 1 over 16. We were given the odds against. We were able to then find the odds in favor, which then allowed us to find the probability that the horse wins the race. Okay, so there you have it. Let me pull this back up again. The tablet's always a little awkward. Okay, so that goes over the section where we're talking about events not occurring, we're talking about or probabilities, and then we talk about odds. So remember, not happening. So the odds that something does not occur is going to be 1 minus the probability that the event does occur. Or probabilities, you've got two situations. You've got mutually exclusive, and then you have not mutually exclusive. When you're dealing with mutually exclusive events, those are the events that could never happen simultaneously. You just add the two probabilities and reduce. If you're dealing with not mutually exclusive events, those are events that could occur simultaneously. So that's where you add the individual probabilities, subtract the overlap, and then reduce. And then you have odds. You have odds in favor, odds against. Odds in favor, you want to look for the way something does happen, divided by the ways it doesn't happen. Odds against, you just flip it upside down. You do the ways it does not happen, divided by the ways it does happen. All right, so that's it for this section. If you have any questions, send me an email.